An LLM judge can flip its winner when answers change order or length. We'll run swap order and verbosity perturbation tests before its scores reach your eval gate. After this, you'll understand how to assemble a pipeline that flags answer rankings with order and length bias. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams use an LLM as a judge to rank candidate answers or label quality. It feels powerful because a single model can score many responses. The hidden risk is that the judge itself has preferences that are not about quality. It might favor the text that appears first or the longer answer. That creates a silent failure mode where your ranking amplifies the judge's quirks instead of true quality. At a basic level, we want two things. 1. Detect when order flips winners. 2. Detect when added words change scores. If we can catch those effects early, we can gate a model from promoting the wrong candidate. Imagine running these checks in a CI job that blocks a release if the judge shows clear ordering or verbosity bias. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we will move from idea to a minimal test that measures first position bias before any ranking decisions are trusted. This snippet measures whether the judge tends to reward the first visible answer. A judge can look stable overall while still drifting toward the left or first option, so the first pass is deliberately simple. The judged rows represent logged pairwise decisions with a left answer, a right answer, and the winner. First wins counts how often the winner equals the left side answer, and rate turns that into an easy release gate signal. Walk through how rows are grouped, how the left label is compared to the winner, and how that ratio becomes a single metric you can threshold. The printed output shows the first position win rate, which tells you whether the next checks deserve closer attention. We saw a potential left side bias. Next, we need to check the same matchup when the answers swap sides to see if the judge is inconsistent. This example checks whether the same matchup keeps the same winner after the answer order is swapped. The important move is by pair, which collapses A versus B and B versus A into one comparison key. Each key stores the set of winners observed for that matchup. So a set with one winner is stable, and a set with two winners is suspicious. Describe how the grouping builds a small dictionary of matchups, and how you compute the set of winners per key. Consistency summarizes how many matchups passed that swap test. The visible output shows swap order consistency, which is a stronger bias signal than a raw average score alone. If some matchups flip when swapped, we shouldn't let those votes decide rank promotion. The next step is to filter to stable comparisons only. This code keeps biased comparisons from flowing straight into a model or prompt ranking. Instead of using every log judgment, clean includes only matchups where the winner stayed the same across swapped order. The wins table then counts victories from that filtered set, and leader selects the best remaining candidate with deterministic tie handling from sorted wins. Explain why we drop unstable pairs, even though that throws away data, and how sorted tie handling prevents non-deterministic promotions. The printed result shows the current release candidate based only on stable wins, which is a conservative but safer choice for a release. Even with stable orders, the judge might reward verbosity. We need a controlled perturbation that pads answers and measures score change. This snippet tests whether longer wording changes judge scores when the underlying answer quality is meant to stay controlled. Score runs stores each candidate with a base score and a padded score variant. So lifts isolates the score change caused by added verbosity. AVG lift gives a compact run level signal, while worst points to the candidate whose score moved the most. Walk through how a padded version is generated, how you compute the difference per candidate, and why averaging across candidates gives an overall verbosity lift. The printed output shows the average verbosity lift and the most affected candidate, which helps catch length bias before ranking decisions harden. With first position and verbosity checks in hand, we can turn them into a single gate that decides if the evaluation is trustworthy. This example turns the bias checks into a small release gate instead of leaving them as ad hoc diagnostics. Checks captures 3 conditions: enough swap consistency, low verbosity lift, and enough clean comparison coverage to rank with some confidence. Passed is the single decision an experiment tracker or CI job can store, while failed preserves which checks need investigation. Explain how raising the consistency threshold makes the gate stricter, while lowering the verbosity threshold catches smaller length effects, and why you want both coverage and stability checks. The visible output shows whether the evaluation passes and how many checks failed, which makes the judge audit actionable. In short, an LLM-Judge position test flags left side and length preferences, not just raw scores. Use swap order checks and verbosity perturbations before trusting a ranking model. One caveat: filtering to stable wins can reduce data and delay confidence for low-volume comparisons. A practical next step is to tighten the release gate by raising the swap consistency threshold and rerunning the evaluation on your full answer pool, so you measure how much coverage you lose versus how much bias you remove. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.